So this is an area where chemistry overlaps a bit with physics. So we need to talk about light. Light is a form of electromagnetic radiation, which consists of electric field and a magnetic field. And these are waves that travel through space, and they're perpendicular, so at right angles to each other. An electric field is a region where an electrically charged particle would experience a force. A magnetic field is a region where a magnetized particle would experience a force. All electromagnetic waves move through space at the same constant speed. That speed is known as the speed of light. 3.00 times 10 to the 8th meters per second. We'll be using that a little bit. If you need it on an exam, I'll give it to you so you don't have to work on memorizing that. How fast is that? Because meters per second, we just don't really have a good grasp of that. In miles per second, that's 186,000 miles per second. That's fast enough to circle the Earth 7 times in 1 second. Right? Light is really fast. Here's an illustration of those magnetic and electric fields. So here we have the electric field component traveling through space, and then the magnetic field is perpendicular to it. I think we've all observed that during an electrical storm, you see the lightning, and then you hear the sound of it, the thunder, later. They don't come at the same time. And that's because sound travels slower than light does. So the sound and the light initiated at the same time in the same place where that lightning bolt was occurring. But we are not right there, thankfully, or we'd be dead. And so we experience the light from it and the sound at different times. So sound typically travels around 340 meters per second, whereas light travels at, I think that's 300 million meters per second, so much faster. And so this is why you can estimate how far away a storm is by counting the seconds between when you see the lightning and when you hear the thunder. So we need to learn a little bit about the characteristics of waves. There are different parameters that we could use to describe waves. One of them is the amplitude. That's how high the wave is. So the wave is oscillating above and below sort of a baseline. And so the amplitude is how high above or how low below it goes. Amplitude is a measure of the intensity of the light. So a bright light has a larger amplitude and a dim light has a lower amplitude. Another thing we can measure about waves is the length of the wave, called the wavelength. And this is given the symbol lambda, which looks like an upside down lowercase y, but it's a lowercase Greek L, lambda. This is the distance from one crest of the wave to the next crest, the length of a wave. One wave, let's do it this way. One wave, let's try that again. Let's do a little fatter. So one wave is from here to here. It's one wave, the length of one wave. Any questions yet? Yes? Yeah, the wavelength is actually, we're a lot more concerned with the wavelength than the amplitude. And we'll talk a lot about that. Any other questions? So the wavelength has to do with the color of the light. And so when we see different colors, we're seeing light of different wavelengths. So a red light is going to have a longer wavelength, yellow light is kind of in the middle, and blue light has the shortest wavelength. The amplitude determines the brightness or dimness. So a dim light, low amplitude, a bright light, high amplitude. But you could have red light that's dim or bright. The wavelength is what determines the color. Another parameter or characteristic of waves is the frequency. And this is given the Greek letter nu, which looks a lot like a lowercase v. It's not v. Frequency is the number of waves that pass a point in a given period of time. The units for this are hertz or cycles per second. And so 1 hertz is 1 per second, one thing per second, whatever you're measuring. Could be the revolutions of an engine. How many times does it turn over? How many hertz? It's used for a lot of things. So I'm going to be drawing a bunch of ugly pictures today. So one way to think about this is think about a person at the beach, right? And at the ocean, there are waves, right? And so the waves are coming in and crashing at your feet. The frequency would be you're standing there and you count how many waves run into you in maybe 5 minutes. And you would take the number of waves divided by the number of seconds that you observed, and that would be the frequency of the waves. How many pass per second? The energy of light, of electromagnetic radiation, is proportional to the amplitude, how tall they are, but also to the frequency. And we can kind of think, again, the ocean can help us understand this, because ocean waves have a lot of characteristics that are the same as electromagnetic waves. They have an amplitude, how tall they are, and they have a frequency, how fast they hit you, and there's a wavelength, how far between them. So the higher the amplitude, the more force the wave has. And so if you think about it, a really big wave crashing on you versus a little tiny wave, are you going to notice a difference in the impact that wave has on you? Of course. A big wave can actually knock you over, right? And a little tiny wave, you just don't even really notice. The high amplitude has a lot more energy, right? The frequency is related to that as well. Actually, it hits you with more force. The more frequently the waves strike, the more total force there is too. If the waves, maybe some medium-sized waves, and they're just coming like one every 30 seconds or something, like, yeah, no big deal. But if they were hitting you every 2 seconds, you'd be taking a pounding, right? There's just a lot of force and energy being dumped on you. So higher frequency, higher energy. Any questions? Well, if the waves are traveling at the same speed, then the shorter the wavelength, the more frequently they will pass. So here's 2 waves. This one has a long wavelength. All right, this is the wavelength. And this one, a little bit irregular, but has a short wavelength. If these are traveling at the same speed, and you're standing over here, if they're traveling at the same speed, this one's going to hit you more frequently, right? And this one is going to hit you less frequently. So there's a relationship between the wavelength and the frequency, and it has to do with the speed at which the wave is traveling. So the speed of light is constant, which makes things very convenient. So we can write an equation like this. The frequency of light is equal to the speed of light divided by the wavelength. So if the wavelength is smaller, the frequency is larger. If the wavelength is larger, the frequency is smaller. They're inversely proportional. The color of the light is determined by its wavelength or its frequency. The wavelength and the frequency are related to each other. If we know one, we can calculate the other. So what we refer to as white light is a mixture of all the colors of visible light. And this is like the light that comes from the sun or from an incandescent light bulb is considered white light. It has all the colors in it. And those colors form a spectrum. And they go red, orange, yellow, green, blue, indigo, violet. A rainbow always has the colors in the same order. And here we see the white light being separated by a prism. There's red, orange, yellow, green, blue, indigo, violet. You should really learn that order. Roy G. Biv. It's a weird name. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Don't ask me what indigo is. I'm not really sure. It's like between blue and violet. I don't know why it deserves its own name, but whatever. So when we observe colors, what's happening is that the light is striking the object, and the object absorbs some of the light and reflects some of the light. So in this picture, this girl has a red shirt on. The light in the room strikes her shirt, and some of it's absorbed, and what is reflected is the red light. And so the red light travels out, and our eyes catch that, and we see that as red. If an object is blue, it's reflecting blue light. Yeah.
What makes it reflect?
That's a good question. What makes it reflect light, and why does it reflect some colors and not others? That's a very complicated answer, very complicated. It does have to do somewhat with the electrons and with the molecular structure of the different compounds in whatever you're looking at. So a lot of our clothing is colored using dyes, right? And dyes are typically organic compounds. My sweater is, fuchsia. If you look at foods, right, especially food for children is all highly colored, right? And you can look at the ingredients, and it'll tell you what food colors are in there. And so there might be a red and a blue, and yet the thing is purple, because those two dyes together are going to reflect blue light and red light, and when we see those colors mixed together, we see purple. And you can change the color of some things by just a small change in the molecular structure. Some compounds will change color in response to heat or pH. It's very interesting and complicated. Yes?
So some animals can only see like certain colors.
Mm-hmm.
We can see more. If we have more like cones or whatever, it makes you see color. We potentially see others. Are there other colors that we can't perceive?
That's a good question. Some animals can see limited colors, and actually some people can as well. And then I've read about people who see more colors than most people can see. I don't know a lot about that, but I do know a little bit about color blindness because 4 of my 5 sons are slightly colorblind, the red-green kind. And so what happens is there are colors that they cannot distinguish from each other. They just look the same. A person who's colorblind does not see the world in black and white. They just don't perceive the colors the same as we do. And so like a couple of my boys, there was a game at Vacation Bible School, and they threw a bunch of colored paper clips in the green grass, right? They couldn't find the red ones. They couldn't see them because they looked the same color as the grass. Now, what color that looked like to them, I don't know. That's, perception is really tricky. But different species of animals, insects, humans, we perceive light differently depending on our biology and how we're detecting that light. It's an interesting field of study. Let's do a little calculation here. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. So we need the relationship between wavelength and frequency. So the equation that we were given is that the frequency is equal to the speed of light divided by the wavelength. And I told you what the speed of light is. It's 3.00 times 10 to the 8th meters per second. And they're telling us what the wavelength is. It's 515 nanometers. Are those units going to work out? No, they're not. I have meters here and nanometers. I need them to cancel out to get a unit of per second. So I need to convert this. I think the easiest way to convert that is just to remember what nano means. Nano means times 10 to the minus 9 meters. So you can write the mathematical meaning of the prefix in there instead of the prefix. And you don't actually have to do any big calculation at all. Now that's not proper scientific notation, but your calculator doesn't care. So we can take what I was doing last night, 3 EE8 and divide it by 515 EE minus 9. And I'm going to get 5.825 times 10 to the 14th. And the unit is per second, which could be written as 1 over seconds, or s to the minus 1, or hertz. Should have 3 sig figs, and so we'll say that this is 5.83 times 10 to the 14th hertz. It's the frequency of the light. Any questions?
Do some textbooks have different levels for V equals F lambda?
It is possible that different textbooks or different fields of study even might use slightly different letter variables for the different parameters. But these are pretty standard. Nu for frequency, C for the speed of light, and lambda for wavelength. So, visible light has a spectrum. There's a rainbow of colors. And when we see a rainbow in the sky, what's happening is that water droplets in the air are acting as prisms and separating the light from the sun into the different colors. So there's visible light, but then there's a lot of other electromagnetic radiation that we cannot see with our eyes. And so that's the entire electromagnetic spectrum. There's radiation that has a shorter wavelength, a higher frequency, and higher energy than light, and there's some that has lower energy than light. So the shorter wavelengths, the higher energy, would include things like gamma rays. Gamma rays are the type of electromagnetic radiation with the highest energy, and they're very damaging to biological molecules. It's called ionizing radiation because when this radiation hits molecules, it can cause them to ionize, to form ions. Ions have different chemical properties than molecules, and so that can mess up the chemical reactions that are occurring in the body. Radio waves have the lowest energy. So when you pick up a radio station in your car, that is the same type of energy as light. It's just a much lower energy. It's got a very long wavelength and is short, a low frequency. Yes, AM and FM are a little bit different. So here's the electromagnetic spectrum. Radio waves are down here. AM radio waves are the longest wavelength. FM and TV signals are in here. Cell phone signals are up in here. So this whole range here is called radio waves. We've got microwaves, infrared, visible light, ultraviolet radiation, X-rays, and gamma rays. So there's energy, frequency, and wavelength, and they are all related to each other. So we have 3 different scales here. The energy is not specified, but this is low energy to high energy. Here's the frequency going from low frequency to high frequency, and the wavelength going from long wavelength to very short wavelength. What's sometimes confusing about this image to students is this part down here. This shows the wavelengths of different colors of light. So red light is, in the 700s of nanometers, and blue light is up here, 450 or so. This part of the graph or the chart comes from this little tiny section here. So it's just expanded at the bottom so we can see it because we're especially interested in this. What this does not mean is that red light has the same wavelength as radio waves, or that violet light has the same wavelength and energy as gamma rays. It does not. The wavelength, the energy for the violet light is over here in this little tiny part. Okay? So your book has some nice descriptions about these. I expect that you will read those. We should know the order of these different types of radiation. So with visible light, the way I remember this is I write down Roy G. Biv. So here's R, and there's the V. And so next to the red light side is the infrared, it's below red. And on the violet side is ultraviolet, it's above violet. Microwaves are the next lower, and then radio waves are the lowest. From ultraviolet goes more energy is X-rays and then gamma rays. Can ultraviolet rays damage your skin? Yeah, they can give you a really bad sunburn. Right? They're higher in energy than visible light. Anybody have any questions? Mm-hmm.
So all of these waves are like the same thing, they just behave differently?
They are all the same kind of wave. They have different wavelengths.
So like if you took light and slowed it down, it would make sound?
If you took light and slowed it down, would it make sound? Sound waves are different.
So that it's not all the same?
So, but sound waves aren't on here. Radio waves are not sound waves. Yeah. It's an electromagnetic radiation that you need a radio to interpret into sound. So a transistor radio has a transistor in it that takes the electromagnetic radiation and changes it into sound. Yeah. And FM and AM stands for amplitude modulation, and FM is frequency modulation. And so the way radio waves communicate sounds is the device that's sending them out will vary either the amplitude or the frequency of the radiation. And then the transistor radio picks that up and reinterprets that, and through a speaker sends it out as sound again. It's really neat. Anybody else have any questions? So we can use a prism to separate wavelengths. So here's a classic triangular prism, white light coming through on one side, and as the light travels through the interface between the material of the prism and the air, it causes the light to bend, and the light will bend differently depending on its wavelength. So the light passes here, and then it bounces and passes out again, and through those corners that it takes, the red light and the violet light get separated, and we spread it out into a rainbow. And this is called a continuous spectrum. All the colors are there. We can also use other sorts of radiation, infrared light. So this is actually a picture of me and my daughter a few years ago. We went to the NASA Jet Propulsion Lab in is it Pasadena? Down in SoCal. Very, very cool. But they had this camera set up, and so a camera using regular light and a camera using infrared light. And so what the infrared camera does is it senses the heat that's coming off, because when things give off infrared light, that's heat energy. And so we see here that our faces, our skin, it shows up as red. That's how the computer interprets these. And the background here is blue, and yellow is less warm than the red, and this is what we looked like at the same time. So thermal imaging is what's used in night vision goggles or cameras. Now, how can you see in the dark? Well, you can't really see in the dark, but you can detect infrared light, which is not visible light. Infrared light is present even in a completely dark room. So if you had a completely dark room and a person standing in it, you could see them with a camera like this because they are a different temperature than their surroundings. And police can use this, and search for people out in the woods and find people because of their thermal image. Any questions? High energy radiation, such as gamma rays, can be used to destroy tissue in a beneficial way. So, cancer is a big problem. The problem with cancerous cells is that they're growing out of control. And sometimes you can do surgery and remove the tumor, the cells that are growing out of control. Other times the tumor maybe is in the middle of your brain, where removing it surgically would do more damage than leaving it there. So how can you treat it? Well, you can use radiation. The problem with radiation, of course, is that it damages all the tissue that it goes through. So what they do is they take small amounts of radiation and target the tumor from different directions. So send a beam of radiation from this direction and from this direction and from this direction, and typically it'll go in a big circle or a half circle, and it'll go from all different directions, and all of those beams will hit the tumor. So the tumor will get hit a whole bunch of times, but the healthy tissue around it will only get hit once. So a tiny bit of damage to the healthy tissue, a lot of damage to the tumor. So that's a medical application of radiation. So we need to understand a little bit about how waves interact with each other. They can interfere with each other, and this can be in a constructive way or a destructive way. So here we have two waves that are in phase. In phase means that their peaks line up and their troughs line up. They have the same frequency and their wavelengths are the same, and they're traveling at the same speed, and their peaks line up. So if these two waves get in each other's space, they will add together and make a wave, same frequency, but now a higher amplitude. And if we have waves that are exactly out of phase, where the peak of one lines up with the trough of the other, when these interfere, they will cancel each other out. And that's called destructive interference. This is similar to what happens on a trampoline, where if you're bouncing just right with another person, they can send you flying, right, all of a sudden. Or sometimes you just stop dead, like what happened? Well, the waves that you're both creating interfered and canceled each other out. This is also the idea behind noise-canceling headphones. So the headphone takes in the ambient sound and changes the phase of it, moves it a little bit so that it's out of phase with the rest of the sound coming in, and that can cause that sound to not necessarily completely disappear, but be much less noticeable.
How do we know when it's going to do, like, which one?
Well, yeah, how do we know what it's going to do? Well, we have to observe its interaction. Yeah. You can observe these sorts of things in water waves. In fact, one of my very fond memories from high school was in physics class. We had these wave tables. It was a shallow container of water with a glass bottom that was elevated above the table, and it had a light. You know, we had these little wave generators, and it would make waves. And the light shining through the water, you could see where the waves were down below, and you could even draw it with on the paper. And if you get two wave generators in there, you could get the waves to interfere. And if they constructively interfered, you'd see bigger waves, the brighter and darker color. And then if they were destructive, the waves would disappear. Very fun. Of course, by the time we got to the end of that section, you know, that module or whatever, the water was kind of nasty, right? Because it wasn't chlorinated or anything. I look back on that and I'm like, ooh, yeah. Another thing that waves do is diffraction. When waves encounter an obstacle or an opening in a barrier, they will bend around it. So, you know, a radio station is sending out waves. Here we are inside of a building. How do the waves get in? If you're standing behind a tree, does that mean you can't pick up that sound anymore? Or with light, you know, light coming through a doorway, does it just stop there and absolute darkness everywhere else? No, it scatters and bends and gets around. So diffraction is when the waves encounter an obstacle or an opening where the size of that is about the same as the wavelength, and they will bend around it. Traveling particles do not do this. So if we have two slits for that light to pass through, then we'll get two bent light patterns that are in phase, and then they will interfere with each other. And that interference pattern that's produced is characteristic of all light waves. So it looks something like this. So here's a barrier with a slit in it, and here's the waves coming at it. And the lines here are representing the crests of the waves. And so it's going up and down and going towards this opening. This opening is about the same size as the wavelength. And so when the wave hits this, it will bend, and now we're going to get waves coming out that are curved. What particles do, imagine throwing baseballs, it's baseball season. Throwing baseballs at a wall, if the baseball hits the wall, it's going to just bounce back. If the baseball hits the hole, it's going to go straight through. Going straight through the hole, does that affect how the baseball moves afterwards? No. It's either going to be stopped by the wall or not, And if it goes through, it's just going to keep going like it would if there was no wall. So particles and waves behave differently when they encounter a slit.
So it would be different for different frequency waves?
Yes. Yeah, so you'll see slightly different effect with different frequency of waves, or if you change the size of the slit.
So if it's a VHF, then it won't go behind the tree?
Yeah, so there's the reason that AM radio, you can pick up AM radio stations like from thousands and thousands of miles. They have a longer wavelength and they're better at bending around stuff, right? And so FM radio stations don't broadcast as far. And so, yeah, UHF, VHF, those are different. And then, of course, you have your TV remotes, and there's a radio one, and then there's the infrared. And infrared, if you've got an object in between, it won't communicate. Although you can bounce it like off the ceiling, past a barrier. That's always kind of fun. What if we have two slits? So here we have a single light source. So the light coming here is all in the same phase. And as the light hits this slit, it's going to diffract. And light hitting this slit is going to diffract. And now we have two new waves, same wavelength, same phase, but as they spread out, they're going to run into each other. And where they hit out of phase, they're going to make a dark spot, and where they hit in phase, they're going to make a bright spot. And so what you see on a screen over here is a series of bright and dark lines. It's an interference pattern. This is one of my favorite science videos. Come. There it goes.
What is light?
What is light? What is light? That's a good question.
There's no separate.
What is light?
Isn't it
Nice.
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are. It's black.
Okay, that didn't go well. Try that again. There we go.
What is light?
What is light? What is light? That's a good question, isn't it? What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are.
It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The color.
It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right?
Yeah.
It would be the diff.
I thought it was off or something.
Okay. Major technical difficulties this morning, and I can't even get the mouse cursor to show up. It's supposed to be a touch screen. Okay, let's try that again.
What is light?
What is light? What is light? That's a good question, isn't it? What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are a light.
Yes, they are.
It lights up the room. It makes it not dark.
What's the difference between blue light and red light?